see any loose connections.
No sign of a coolant leaking either.
I guess the motor's had it.
Another production unit has failed.
Billy, that's not funny.
You two are finished. Coffee's nearly ready.
At least your heater is working.
Oh, good.
We have one of those out in space, too.
Well, I certainly hope so. There'll be no product at all if the thermal control systems fail.
There's nothing wrong with the thermal control system. Wilhelm checked it out himself. And you know what a perfectionist he is.
Thank you. Usually I try to be so, but...
What?
Well, perhaps I should have looked into the system more thoroughly. What worries me is that I may have been distracted.
Distracted?
By what?
Well, as you know, I consulted the aerospace company to find out the best system. They arranged for me to meet Dr. Seymour, the head of their thermal design department.
Mr. Schroeder?
Ah, good morning. I have an appointment with Dr. Seymour.
That's me. How do you do?
Oh, good morning. Beg your pardon. Are you
The head of the thermal design department, that's right. Shall we go to my office? Just come from Frankfurt.
Yes.
Have a pleasant flight.
Yes. Well, I don't wish to sound foolish, but I didn't expect to meet a woman, especially one so...
Attractive?
Well, yes.
But you have an attractive wife, Wilhelm.
Oh, yes, of course, but I'm still not used to working with attractive women. Women engineers, that is.
The cooling system is based on a fluorinated hydrocarbon coolant, similar to that used in domestic refrigerators. It's pumped at high speed and passes through panels like these. They radiate maximum heat into space and reflect any light that falls on them. Valves allow the coolant to pass through varying numbers of panels in order to control the amount of heat lost. Are you with me?
Oh, yes. Yes.
The coolant loop passes through these pallets, which hold the payloads. Each payload is attached to what we call a cold plate. The user can dispose of surplus heat via the cold plate.
I take it we must provide our own thermal control inside the production unit.
Yes.
That's where I need your advice. Let me show you. We have an electrophoresis apparatus in which we pass a high voltage current through liquids. There are several other minor heat sources, such as electric motors. What kind of cooling system would you suggest?
Every space package has to be insulated by a thermal blanket. As you can see, it contains layers of material separated by several layers of mesh, which minimize the amount of heat loss by conduction. The silver surfaces reflect heat from inside the payload and from outside.
Both ways.
Oh, yes. Because on one side of the package facing the sun, you have very high temperatures. And on the other side, they're close to absolute zero.
The outer layer looks like gold.
That's a plastic film of captain. It's stable over a wide range of temperatures and doesn't degrade in ultraviolet light. It's rather beautiful, isn't it?
Very beautiful.
Inside, the payload components are usually coated with a matte black paint, like that, in order to radiate heat to the cold plate. Well, that should be enough to deal with minor sources of heat, such as your motors.
What about the electrophoresis unit?
Oh, that'll need more thought. Should we talk about it over lunch?
Lunch? Oh, yes. Thank you very much. So, that's how Stan and I reached agreement. Thank you very much.
So what sort of cooling system did you have in mind?
Oh, a pump and a coolant loop. Look, suppose we take a loop from the pump around the electrophoresis plates, then down to your cooling plates.
That could work. We call that an active system because you need a pump with an input of energy and a control system.
Is there any other way?
Well, if you give me all the relevant data, I may be able to suggest an alternative. Then it will be up to you to decide. Of course, you will need an auxiliary heater as well as a cooling system.
Why?
When your unit is not in production, during launch and retrieval, for instance, it won't produce any heat. You'll need an alternative heat source to prevent your liquids from freezing.
Oh, yes, I should have thought of that. I must say, she had the most wonderful smile. Anne is a first-class engineer, you understand.
Anne?
Dr. Seymour, she asked me to call her Anne. And she called me Wilhelm. But it's usual among professionals in England.
Oh, really?
Of course it is, Willem. He's only teasing.
Ah. Anyway, I asked her about the sensors we would need to monitor the temperatures and flow rates, and she suggested a specialist firm.
This is a temperature sensor, Mr. Schroeder. It senses temperature by change of resistance. It can measure temperature over a very large range and can be used in many different environments. Full specification, here.
Oh, yes, this is very helpful. I believe you know Dr. Seymour.
Anne Seymour. Yes, know her well. Excellent engineer.
Yes, yes. She said that you could help me in another matter. We have to monitor the rate of flow of liquids in the production unit.
What sort of flow rates we talking about?
Well, not very large, say 200 milliliters per hour.
200 milliliters per hour. And what's the diameter of the tube?
2 millimeters.
Let me see now. That gives us an average velocity of 17.68 millimeters per second.
Obviously, we can't use a mechanical system like a turbine.
Not in a tube that size.
What about ultrasonic sensors?
They're not very accurate at low flow rate. What you need is a constant temperature anemometer.
A constant temperature?
It operates by maintaining a probe at a constant temperature within a Wheatstone bridge.
Forgive me, I am...
Let me draw it for you. This is the Wheatstone Bridge. 4 resistances arranged so, with a current applied at the bridge end. Now, the bridge is balanced when the ratio of these pairs of resistors is equal.
I see.
At this end, we have a heated velocity sensor. It's kept at a higher temperature than the fluid flowing past it. So when the fluid flows faster, it'll transfer more heat from the transducer.
And if it flows slower, it'll transfer less heat.
Correct. Now, at this end of the bridge, we have a thermal sensor that's measuring the temperature of the fluid.
So that compensates for any fluid temperature changes?
You've got the idea. The system maintains a constant balance between the transducer and the fluid. So if the fluid velocity changes, we get an error signal across the bridge. A servo amplifier varies the electric current until it restores equilibrium. Those variations in the current are a direct measure of our flow rate.
How fast does the system operate?
Fast enough to give an analog signal that's virtually instantaneous.
We're concerned about the size and weight. How big is the equipment?
Here's the anemometer we'd insert in your tube. And here's the amplifier which gives us the signal.
I asked him to design a system to meet our requirements, and 3 weeks later I went back to see what he had to offer. Thank you her again. She was doing some work on the project, and, well, she said she would contact me.
Morning, Graham.
Morning.
This is the apparatus we use to calibrate the sensors, Mr. Schroeder. Here we have a fluid, and here we have a laser anemometer.
A laser.
The laser beams intersect. Now, the fluid is seeded with particles which scatter the light. If the flow rate increases, the particles move faster, and the frequency of the light is shifted by the Doppler principle. This shift is monitored by the photomultiplier, and the flow rate is shown on this digital readout.
Can you measure a Doppler shift if the change in the flow rate is very small?
Yes, even if it's only a fraction of a milliliter per second. The laser is 99.99% accurate.
Pity it's too big for our production unit.
In any case, you'd hardly want to seed your vaccine with impurities, Mr. Schroeder.
That is true.
Here is our constant temperature anemometer. The reading from that is shown on this digital readout. Start the pump, Graham. We shall calibrate and certify every sensor, Mr. Schroeder, and we'll supply you with a calibration matrix.
A matrix.
You enter the matrix in the memory of your processor, which then compares it with the incoming data and gives you instant warning if there's any discrepancy.
It's very impressive. Ma'am?
Excuse me. McFarlane? Hello. Yes, he's here. It's for you, Mr. Schroeder.
Hello, Schroeder. Oh, Anne, hello. How nice to hear from you again.
I've been working on some ideas for the project. Can you come over here today?
No, I can't get there till this evening. Perhaps you'd like to join me for dinner tonight.
Well, you invited me last time. It's my turn. Why don't you have dinner with me at my home?
I'd like that very much.
Don't stop now.
Did he go to her place?
Oh, yes.
Wilhelm, how nice to see you. Come in.
These are for you.
They're lovely. Thank you. I've been working on your electrophoresis system. I do quite a lot of work at home. It's so much quieter here. This way. According to your figures, it's possible to use a passive system to cool your electrophoresis apparatus.
A passive system?
Heat pipes from the electrophoresis plates to the cold plate. This is a heat pipe. It's sealed at either end and contains ammonia. And this is what it looks like in section. The ammonia evaporates to take up heat, and the gas travels down the pipe to the cold plate where it condenses like any other coolant. The liquid then travels back again along these narrow grooves. This is very efficient in space because there's no gravity.
So there's no pump. That's why you call it passive. It's very interesting. Do you recommend this system?
A passive system is always preferable to an active one in space. Because there's no pump, you reduce weight and use less energy. What's more, there's nothing mechanical to go wrong.
I'm sure you're right. You've totally convinced me.
Good.
So now I know what you mean by distracted.
I have checked the record very carefully. It shows that the thermal control system has functioned perfectly. As soon as the electrophoresis unit cut out, the heater increased its output to compensate. All the sensors show an optimum temperature throughout.
Of course they do. Even if you weren't totally objective, you still chose the best system.
I hope so.
But sometimes you surprise me, Wilhelm.
What surprises me most of all is that, well, Anne,
Found you attractive too? Well, that's not surprising. It's not surprising at all.